That's exactly what the question says. It says find a complex number. In fact, the question says find all complex numbers such that they are the solution to this algebraic equation. We're going to discuss with you the solutions to algebraic equations a bit with more details later, but this particular one we can solve already with our knowledge of the trigonometric and exponential forms. And I'm going to do it right now on the slide. Already on my picture, on this, you see I have this picture here. The blue vector, it's effectively my negative 27 number, represented as a vector or as a complex number on a two-dimensional plane. So the length of this vector, negative 27, I'm not going to make it marking. I'll mark it later maybe. All right. Well, when I'm in my solution here, I will do it in two-stage approach. First, I will make a very quick substitution because this expression under the here inside the bracket, it's something I don't want to deal with all the time. So I will make a quick substitution. I will introduce a new unknown. I will call it W, which will be just the abbreviation for the expression in the bracket. And then my equation becomes as simple as this. So effectively, what I'm going to present now is the way we take cubic roots of complex numbers. Because negative 27, even though if essentially it's a real number, it's a real number, negative integer, but still it is a complex number. And now we're going to just see how we take the roots of the complex numbers within the complex number scope. It's again an example where the exponential forms or trigonometric forms are useful. So look what I'm going to do. I'm going to just convert everything here to the exponential forms. For the W, I will use the symbolic form. So R will be the absolute value, and theta is the argument. And if I do so, we know what happens when you raise a complex number in trigonometric form to a cubic power, right? Something like this happens. The W cube will take such exponential form. I mean, this exponential form. You will cube the modulus, and you will triple the argument. Negative 27 is my conversion of the negative 27 to exponential form. I separate the negative. Then 27 becomes the modulus of this complex number. And for the negative 1, I have a very particular choice of the exponential form. Here it is, ei pi. And I made another conversion. I just made the observation at 27, it's a 3 to the cube, which will be handy in a second. Right, so here we go. And now I'm going to sub in now everything. I'm going to sub in my exponential forms into this equation we're solving. Easy substitution. You see I'm using the exp notation. I alternate them from time to time. Essentially, these are the identical numbers, but in terms of the presentation, sometimes one is better than the other. Obviously, when you use the little e with the superscript, it takes less space. When you use the exp, it takes more space, but it's more visible what the argument is. So when the argument takes a complex form, like a fractions or pluses and minuses, I use the exp to make it more visible. When the arguments are not so important, or when they are small and visible even in these smaller notations, I use the e letter. So I'm changing the notations only because it's just for the exposition purposes only. Mathematically, nothing is different between these two. So here's my equation in exponential forms, and now we can equate modulus to modulus and argument to the argument. If I do so, I will come up with the immediate solution. Here it is. Modulus should be 3, and the argument should be pi and 3. At this stage, you may think we can stop the solution, but actually there are something we overlooked, because when I converted my negative 1 to exponential form, I chose this particular one. In fact, I have some other options for this exponential form. For instance, I can take for the number negative 1 as its exponential form, I can take the number like this. Let me just move this a little bit. I can take a number like this. I added up one full revolution, which hasn't altered anything in terms of the cos and sine function. So this exp equally represents negative 1. Equally. It's another exponential form for the same number. It's the same complex number. However, when you equate the left-hand side to this new right-hand side, for the r value, there won't be any alterations. It will be free again, but theta angle this time will take a different form. And this time, this new theta angle, it's different, substantially different from my original pi and 3. The difference is no longer 2 pi between these two. So effectively, we come up with another solution. How many other alterations like this I can do? For instance, I can find another exponential form for the -1, like this. Again, equally legitimate exponential form for the -1. Rather than plusing 2 pi, I'm taking away 2 pi. And yet, if I use this new exponential form, the theta angle for the original w, after I'm taking the cubic root, again will take different value, meaning different substantial, not by 2 pi different from the two first ones. So it is another solution. The question is how many times we can do this sort of tricks, how many times we can alter the representation for -1 by adding or subtracting 2 pi and come and still find a new theta angle here on the right-hand side of my implication. Look, here actually I have another attempt. You see, I add now 4 pi rather than 2 pi. And I'm asking whether they will give me another new theta. Let's just see. This time my theta will take this form. And this time it doesn't bring anything new. Because this time this new theta is essentially my negative pi and 3 theta with extra revolution. Well, the actual answer to the question why exactly we have, well, right now you're probably getting the idea that we only have 3 possibilities for the theta angle, and that's true. The actual logical proof of that, I'm not going to present in class, probably yellow book has it. I mean, the theoretical part of the yellow book has it. What I'm going to state here is just a theorem which says this. Every time you solve an equation like this, z to the power n equal to unital complex number, you see, I'm omitting the modulus from this equation because it's irrelevant to our current discussion. Every time you solve an equation like this, every time you're trying to take the nth root of a complex number, of the unital complex number, you will always have, n is the integer here, you will always have solutions of this form. You see, you take this principal alpha, you divide by n, like here. You see, my principal alpha was pi, I divided it by 3, my alpha by 3, my alpha by 3, and then you have to add up these 2 pi bits divided by 3 or by n, depending what your n is, also. And altogether, you will have possibilities for how many times you can add this 2 pi, n different possibilities. So altogether you will have n different solutions. That's why I index them with a little k as a sub-index. And this little k, which appears here, is how many times we add 2 pi. It will take n different values between 0 and n take 1. Geometrically, if I try to picture these numbers here, let me just first write them out. So basically we solve the equation, we solve this equation. At least in exponential form, we did. The values for r are always 3. The values for theta, we have 3 different possibilities, pi and 3, pi and negative pi and 3. So here they are, all my solutions, and I'm going to index them now. W1 is the first solution. My r and the angle theta from here it is. Or if I convert this into the Cartesian form, using the standard values for sine and cos, here's the conversion. Value W2, this is the angle pi, here it is. Sine pi, cos pi, it's a very simple values, we all know them, it's just -3. And that's actually solution which we know from the real analysis. If you confine to the realm of real numbers alone, we still have a solution for this equation. -3 is the only solution we have for this equation. And it is part of the solutions which we have when we live in the larger universe, in the complex numbers universe. And the last solution, W3, it's again trigonometric form or exponential form with this last angle, -0.3. And that's the Cartesian form of the same solutions. Geometrically, I can picture these solutions for you. Here they are. They all, together, they produce the perfect triangle. For the higher ends, it will be perfect n-gon, like a pentagon. Oh, I don't know the name, the other name. It will be perfect n-gon, depending on your n. And the angles, we all know these angles. This is a pi and 3. This is angle pi. This is -pi3. So this is the, this is a W1 root. This is a W2 root. And this is the W3 root. Now you can probably realize why I have to stretch my blue vector so much. Because the length of the blue vector, 27, and the length of the red vectors is 3. So 27, 9 times longer than 3. Actually, this picture is up to scale, so the blue vector is 9 times longer than the red vectors. And obviously, all of them, they end up on the unit circle. Okay. Here it is.